We're going to meet ion channels in a lot more detail in later segments, but I thought I should give you a brief overview as we start our journey through looking at some of the important proteins we'll meet in the course. So what is an ion channel? Well, a simplistic way of looking at it is as a protein-lined hole through the membrane. As we'll see in later videos that I produced, that's actually a gross oversimplification. I'll show you how an ion channel really works in a later video. But for the moment, it's probably okay to think about them that way. So why do we need a protein-lined hole in the membrane? Well, ions, shown here in blue, are charged, and charged substances cannot penetrate lipid bilayers. So if we want to get ions from one side of the membrane to another, we need something to help us. Now, if we put a protein into the membrane and arrange it so that it's got a hole through the center of the protein, and the amino acids that will interact favorably with our ions line that hole, we've got a way that ions can cross the membrane. Now, ion channels only work via diffusion. They're not active proteins. They don't expend energy to move ions. They will only allow ions to move down an electrochemical gradient. So from high concentration, for example, to low concentration. But they can do this very efficiently. The maximum rate for ions moving through an ion channel is thought to be around 1 million ions per second, and that's 100 times faster than the fastest transporter. That kind of speed is vital when you think about how the mammalian nervous system operates. So we need the speed of ion channels to be able to have a rapidly operating nervous system. So what are the basic properties of an ion channel? Well, if you want to form a protein-lined hole in the membrane, you have to do it with a transmembrane protein. So all ion channels are transmembrane proteins. They all show some degree of selective permeability, so they will only allow certain ions to go through the hole. And their opening and closing are controlled. So this is a process that's termed gating, and there are a lot of different ways in which ion channels can be gated. And that kind of leads on to the other thing about ion channels. They're extremely diverse. Probably not the most diverse class of proteins that we'll meet, but they show a lot of diversity, and we'll see some examples of ion channel families in later sessions. So let's have a think about selective permeability. So there are 4 physiologically important ions that can pass through ion channels: sodium, potassium, calcium, and chloride. Now, ion channels all incorporate a structure called a selectivity filter. The job of the selectivity filter is to allow through ions that are the right size and have the right charge. So the filter needs to be able to distinguish between ions. Now, if we conceive our filter as being a sort of donut-shaped structure, it's relatively easy to see how it could distinguish on the basis of size. An ion that's too big simply won't be able to go through the center of the donut. That's actually a bit of a problem when you think about it, though, because ion channels can actually distinguish between an ion which is just the right size to go through the hole and a very small ion which in theory could slip through very easily. They won't allow the very small ion to pass through. So this filter here is doing more than acting as just a size-based screening device. It actually has to interact with the ion, and it will only allow the ions that form the correct interactions to pass through. Too small, it won't. Too big, it won't. It has to just be right. So the Goldilocks effect. Now, the other job it has to do is distinguish on the basis of charge. Now, it's relatively easy to see how you could do this with cations and anions. If you incorporate some charges into the channel, so perhaps a ring of charge, it will repel like charged ions. So a ring of negative charges in our channel will repel anions and won't allow them through, but it'll attract cations and allow them to permeate. Now, it's also worth thinking about what happens when a channel that's selective for a particular ion opens. So what I've shown you on here are some typical concentrations for ions in a mammalian cell. You'll see this vary quite a lot in different sources, and that's because there's no such thing as a typical mammalian cell. Cells differ quite a lot in their iron gradients. These values are taken from a neuroscience textbook called Baer et al. So outside the cell we've got high sodium. If we open a sodium selective channel, sodium will go down its concentration to the inside of the cell where the concentration is much lower. So we have a concentration gradient that favors sodium entering the cell, and that's going to cause the membrane to depolarize. Potassium has a high concentration inside and low outside, so it will tend to move out of the cell, and that will make the inside of the cell more negative. So we're going to see hyperpolarization. If we've got an ion channel which is sodium and potassium selective, so it will allow both through, and that's actually quite a common scenario, will allow movement of both ions, but the membrane potential tends to favor the movement of sodium out more than the movement of sodium into the cell rather than the movement of potassium out. So we'll tend to see depolarization if we have a sodium potassium selective cell. Chloride is high outside and low inside, so on this slide I've shown you the ionic gradients of a typical mammalian cell. Now I put the inverted commas there because mammalian cells actually differ quite a lot in the various ion gradients that they have. But these values are taken from the neuroscience textbook Baer et al. So they're kind of standard values. So our basic situation is we have high sodium outside, low potassium outside, quite high chloride outside, and quite high calcium outside compared with what's inside the cell. The cell has also got a negative charge on the inside. So let's think about what happens now when we open a channel that's selective for an ion or a combination of ions. So if we open a sodium selective ion channel, we've got high sodium concentration outside and low inside, and we have a negative charge inside the cell. So our cell is going to allow sodium to flood through this channel and the membrane will depolarize. So the charge inside the cell will become more positive. If we open a potassium selective channel, potassium will move from the inside to the outside, and that's going to cause the membrane to become even more negatively charged, so we'll see hyperpolarization. Now if we have a sodium and potassium selective channel, and some ion channels have a hard time telling the difference between sodium and potassium, so this is actually quite a common situation. We're going to see movement of sodium into the cell and potassium out, but at the resting membrane potential, about minus 70 millivolts, we're mostly going to favour the movement of sodium in. We'll see relatively little movement of potassium out. For a chloride channel, high concentration of chloride outside, low inside. So when we open a chloride selective channel, chloride will move into the cell. That will cause hyperpolarization. In other words, the membrane will become more negative. And if we allow calcium to go from outside to inside, very high concentration gradient here, then, well, we can't predict what's going to happen. In some cells, this will cause a change in the membrane potential, but in other cells, we see very diverse effects, and that's because calcium has very important signaling functions in cells, as well as being a charge carrier. So you'll meet these ions a lot more in other videos, and if you're doing excitable cells, we'll go into this kind of thing in a lot more detail. So let's think about gating now. On this slide, I've shown you the basic process. Here's our closed channel, and we want to get it open. So the rule is that most channels are closed most of the time. So the gating process is the process by which the channel opens. And there are quite a diverse range of ways in which channel opening and closing can be controlled. Mechanical, some ion channels will respond to pressure on the cell. Second messenger, we'll meet that in later segments, but second messengers generated inside the cell can open or close ion channels. Some channels have to be phosphorylated by kinase enzymes before they'll open. Some, these leak channels, well, they disobey this rule down here. Leak channels are open most of the time. So what we do with their gating is to close them. Ligand gated and voltage gated, these are two really important classes, and I'm going to go into those in much more detail in later videos. And then finally we've got proton and G protein gated and temperature gated. So we'll see examples of some of these classes in later sessions. So the gating is very important for two reasons. One, it tells us how the channel is open and closed, and secondly, because it often feeds into the naming of the ion channel. So ion channels are often named by the way they're controlled and their ion selectivity. So a voltage gated potassium channel is a channel that's selective for potassium and is opened when the membrane potential changes, when the membrane voltage changes. Now, if we're dealing with the class of ligand-gated ion channels, we name them after their gating mechanism, but we do it according to their natural activating molecule, the ligand that binds to them. So the GABA A receptor is a chloride channel whose opening and closing is controlled by the binding of gamma-aminobutyric acid, and that's a neurotransmitter. So when two molecules of GABA bind to the receptor, the chloride channel opens. We'll meet these channels in a lot more detail in later sessions.